Hello. Archaeologists are often interested in the function or use of ancient artifacts, or even rooms and buildings. It's important to make a distinction between function and use. Function suggests the purpose of a tool. In other words, the purpose for which its maker intended it. One way to think of that is as its designed function. However, tools aren't always used the way that the makers intended. Most of us have used screwdrivers to open paint cans, for example. That doesn't mean that that's the function of a screwdriver. Inferring an original or design function of an artifact tends to be highly uncertain, but we can often do rather better with determining its use, or at least its last use. Use-where analysis is a method that, for the past 50 years or so, has increasingly helped archaeologists figure out the uses of stone tools.
The pioneer of use-where analysis was the Soviet archaeologist Sergei Semenov. When the English translation of his book appeared in 1964, use-where analysis began to be a regular feature in Western archaeology as well. Use-where analysis depends on the fact that when flint tools are used, contact with the materials on which they're used leave microscopic traces that we can see under a microscope. To determine how a particular tool may have been used, we want to compare its use traces to those on experimental tools that we make with similar forms and use them on a variety of materials in various ways.
Use-where analysis involves inferences by analogy. By that, I mean that we compare the use traces on an ancient tool, whose use is unknown, with those on a variety of modern tools, similar to the ancient one in important respects, such as material and edge angle, but whose uses are well documented. Generally, that documentation includes several factors thought relevant to the creation of use traces, such as the material to which the tool was applied, usually called the contact material, the motion of use, the angle at which the tool was held, the amount of pressure applied, and the number of repetitions. Strong similarity between the ancient tool and some of the modern ones in their microscratches, polish, and edge chipping, for example, might indicate that the ancient and modern tools were used on the same material and in the same way. However, it doesn't unequivocally prove it. To make a stronger inference, we need to ensure that we've made comparisons to a wide variety of tools used in different ways, and ruled out most of the competing hypotheses for the ancient tool's use.
Because it involves this kind of comparison, use-where analysis depends on inference by analogy. To use a simplistic example, we might find that experimental tools that we'd use to scrape wood show parallel striations perpendicular to the edge, pitting, and polish on the high points that is similar in many ways to what we see on the archaeological tool. This may allow us to infer that the archaeological tools may also have been used to scrape wood. However, because analogy is inductive, this evidence by itself doesn't give us very strong confidence in our conclusion that the archaeological examples were also used to scrape wood. We would want to do a lot more experiments, including ones on other kinds of materials, before we became very confident of that conclusion.
One experiment, for example, might be to see whether or not a tool that's been retouched with a slightly arcing edge might have been used as a draw knife, perhaps for thinning and straightening a cylindrical shaft of wood. So if you really wanted to make this a serious experiment, it would be a good idea to find some way to hold the stick in place so it's held held still and at a constant angle. But here I'm just going to use it to press it against my stomach here to hold it in place. And you would have the people involved in the experiment then attempt, so you can see why it would be good to have a better setup than what I have here to hold the stick stiller. And you want to try to hold the alleged draw knife at a near constant angle as best you can, and see if you can use it to sort of plane the wood in such a way that it becomes thinner and straighter on this side. And you would do this for a certain number of repetitions, so I would be counting how many strokes I'm doing here and try to keep each stroke at approximately the same angle, or holding the tool at the same angle, and each stroke approximately the same length. And notice that they're always in the same direction. I'm not using a back and forth motion. And it'd probably be a good idea. You notice so far I've mostly been removing bark, I'm just now starting to cut into the wood beneath the bark. So probably a good time to stop, still counting your strokes. Count or stop at a point where the bark is completely removed, and set the tool aside so whoever's examining the tool for use traces can examine what it looks like after the bark has been removed. Of course, you don't tell the analyst that that's the reason why you sent it off to be examined, because just in case the use wear as it develops looks a bit different on the bare wood than it does when cutting through bark, you want to take advantage of that kind of landmark and have it examined. But in this case, we'll just pretend that we had set it aside and came back to this tool after the analyst had examined it under the microscope over here. And then we continue on with another few hundred strokes, perhaps, and then have the analyst look at it again to see what changes there may have been in the use damage on the edge.
Just some of the use motions that archaeologists have investigated include scraping, slicing and incising, sawing, drilling, and penetration, as with a projectile in penetrating the hide of an animal. They also include digging motions, as with hoes. Archaeologists have also investigated a large array of contact materials, only some of which you see here.
There are a lot of things to consider in an experimental design because so many variables can affect the outcome of the experiment. Usually we're interested in exploring one particular variable, what its impact is on something. So for example, if we're doing use wear experiments, we might be interested in determining what kind of polish develops on the edge of a stone tool when it's used in a particular way on a particular material, such as some kind of wood, or perhaps antler or bone. But when we do an experiment like that, we have to be mindful of all the other factors, what we call confounding factors, that can also affect the outcome of the experiment.
If, for example, we're interested in use wear differences that are due to differences in contact material, we should be mindful of a whole lot of other factors that could also affect the character of the use wear. When we have multiple participants in a use wear study, potential differences between them are among the most important confounding factors.
For example, I can take a flint edge, and maybe we decide we're going to experiment with a longitudinal incising motion in one direction using a particular kind of raw material, in this case a Jordanian flint. And we're going to do many repetitions there to see if it forms a distinctive kind of polish that maybe differs from the kind of polish we'd see on antler. Now, among the factors that we'd expect to affect the degree of polish and the kind of polish on that edge is certainly the material, the contact material that we're incising, in this case wood, the raw material, in this case flint, the edge angle on that flint. The shape of the edge in plan view might also be a factor. But other factors would include things like how much pressure I apply when I'm doing it, whether I'm doing it or someone else does it. Also, possibly the shape of the topography of the piece of wood, whether it's flat like this one or curved like this one, potentially could have some impact. Furthermore, if I want to do this multiple times and I switch to another flake, the edge angle and the shape of the incising edge on this other flake is not going to be exactly identical to the first flake that I used. So again, if I get a different kind of polish on this one than that one, when I use it on, say, antler, does that mean that the difference in polish is due to the fact that I used a contact material of antler instead of wood, or is it due to the fact that there are small variations in the shape of the edge on the tool, the edge angle on the tool, or the amount of pressure perhaps that I put on the tool when I did the incising motion. The problem gets even more difficult when multiple people are involved in the experiment. So when I'm making an incising motion, I'll be doing it in a certain way. One of my colleagues might come along and do some motions, particularly since we usually want to do lots and lots of motions and we get tired. We sometimes might take turns doing the different motions. My colleague might incise it in a slightly different way, might hold the tool at a slightly different angle, for example.
We can classify many of these confounding factors as falling into one of several very general categories. The first is history, which can include any changes that occur over the course of an experiment, potentially including even such simple things as changes in light conditions. This can be particularly important when an experiment, including a use-where study, takes place over a very long time. A category that also involves change over time is maturation. This specifically involves changes in either the participants or the materials used in the experiment. For example, participants can become more skilled over time or become more tired over time. There can also be changes in the humidity of the contact material. Instrumentation has to do with changes in the equipment or the people operating the equipment. For example, changing the kind of microscope or the image analysis system or the people doing the analysis could all have an impact on the results. Even decisions about how to clean the artifacts can have an impact on the appearance of the use-ware. Selection bias has to do with the way that tools, people, and contact materials get allocated in the experiment. For example, it would be problematic to allow participants to choose their own materials and tools because the choices that different participants make could have a severe impact on the results. Another category is called experimental mortality. This is most typical of long-lived experiments because some participants tend to drop out before the study is over. But it could also apply to a case where a tool broke before the required number of repetitions was achieved.
All of those things might make very little difference, or they might make a lot of difference. The point is we don't know unless we investigate those things, or we find some ways to control for them. Some we can try to hold constant. For example, if we're concerned about the angle at which the tool is held during a scraping motion, we can actually construct a device that holds the tool at a constant angle so that when we do the scraping motion by rolling it back and forth or something, it's going to be constant angle and perhaps even a constant pressure. We can make some kind of setup that would allow us to control the angle and the pressure extremely well.
One partial solution then is to construct carefully devised jigs that control things like pressure and direction of force.
But lots of times there are things going on in experiments that we can't control very effectively in that way. So the alternative is to control them with randomness. So what we would do in that instance, recognizing that each of the flint edges that we're going to use is slightly different, and that each researcher is going to be slightly different in terms of how they hold the tool, how much pressure they apply, and that sort of thing, we make sure we randomize all of these variables as much as possible.
Randomly allocating tools, contact materials, people, and motions of use helps to get rid of selection bias.
So that each time I'm going to do a certain number of repetitions of a cutting motion on this piece of wood, I would first of all randomly pick one of the flints to make sure that I'm not biasing the result in terms of which flint I'm going to use. So I roll here a 2, so that means I'm going to use this flint, whose cutting edge is this one here, and I might roll the dice again to decide which piece of wood I'm going to use. If I have, in this case, I have 3 different pieces of wood of the same species. This one's kind of small though, but these 2 are maybe big enough to use. So I maybe would roll again. An even number gives me this one, an odd number gives me that one. It's an odd number, so I'm going to use this one. And then maybe also use a random number table or something to decide how many repetitions I'm going to do before my colleague steps in and does some more repetitions, a certain number of times dictated by a random number table. And then either I or somebody else replaces that colleague to do some more repetitions. So those are some of the factors you have to think about in an experimental design, but there are others as well. One is that you need to have a control group, because we want to be sure that when an analyst looks at the edge of one of these tools under a microscope and says, oh yeah, this has got a certain kind of polish on it that comes from incising antler, we want to make sure that that analyst would realize when an edge was completely unused. So the most obvious kind of control group to use in something like a use-where experiment is to have some tools that were not used at all. We would again randomly assign each of the tools to groups, some of which are going to be used for incising antler, let's say, some of which are going to be used for incising wood, and some are not going to be used at all.
For example, we can use a random number generator to assign a bunch of tools to two groups, a treatment group, which gets used, and a control group that is unused.
Our main goal is to see if there's a difference in polish between incising wood and incising antler, but we also have a control group that's not used at all, because if we can't recognize a tool that hasn't been used at all, that would obviously be problematic. The other thing is to have blind testing or double-blind testing. What blind testing means is that the person working at the microscope to look for the polish on the edges of the tool doesn't know to which group the flakes belong.
In blind testing, the analysts who examine the tools for traces of use are completely ignorant of how the tool was used, or even if it was used, or whether it belongs to a pre-test group or a post-test group, terms that I'll explain in a few minutes.
In other words, that would not be me. If I'm the one who's incising the wood and incising the antler, I should not be the one looking through the microscope. That should be some other member of the project who has no idea which flakes were used for incising wood, which ones were used for incising antler, and which ones were not used at all. And typically, you would have a fairly large number of these things done. We would, again, in some kind of random sequence, we would use a great many more lithics than what we see here on the table. We would probably also use a great many more pieces of wood and pieces of antler, all of them randomly assigned in each case. And then the analyst who's looking through the microscope would get a whole bunch of those periodically as the experiment is going on. So we might do, say, 2,000 repetitions, and then the analyst looks at them. And then we do another 2,000 or 3,000 repetitions, and then the analyst looks at them again. But each time the analyst looks at them, she or he is not going to remember which ones they'd seen before and what they saw on them before. And they're also not going to know which ones were used for what or used at all.
The design of experiments can be quite complex, and here I'm only going to describe a few varieties. Some use-where studies use a simple design called the post-test control group design. This involves assigning tools to two groups, only one of which is used, and then comparing them for traces. However, to be sure that any between-group differences are actually due to the uses to which some of the tools were put, we really need to have examined the tools before any of them were used. After all, it's conceivable that there were already differences between the two groups at the beginning of the experiment. This calls for a pre-test post-test design that involves examining the lithics in both groups, both before and after the lithics in one group were used. In this simple example, the tools in both groups were examined prior to the tools in the treatment group being used to scrape hides. To be sure that analysts aren't influenced by any preconceptions, it's important to randomize the order in which the analysts examine the artifacts. It also helps to have more than one treatment group going on at the same time, so that analysts can't guess what it is they're examining. However, there's an even better reason to have multiple treatments in the same experiment, and that's the fact that there can be interactions among the variables in the experiment. Factorial designs allow us to evaluate these potential interactions. For example, instead of having one treatment group, we could have two treatment groups in addition to the control group. In this example, the treatment groups are two different contact materials. With a 3x3 factorial design, we can evaluate not only the contact materials, but also the levels of use. We can gauge level of use by the number of repetitions. Alternatively, we can use factorial designs to evaluate contact material and motion of use simultaneously. The need for blind testing has implications for how we manage a project on use-where. You need to have a manager or allocator who allocates instructions, materials, and tools to the people performing the experiments, and insulates all those processes from the analysis of the tools. For double-blind testing, that allocator also has to be a different person than the one who analyzes the final results of the experiment, as that person should be conducting statistical analyses without knowing ahead of time what the groups represent. Finally, the results of any research group conducting use-where studies need to be replicated by other groups. Consistency among research groups gives us more confidence in the results.
Those precautions allow us to control for these so-called confounding factors. Because an important thing about an experiment is you want to make sure that you're measuring the thing you really want to measure, and that your result of your experiment isn't being uncontrollably impacted by other factors that are not the point of the experiment.
Of course, a very important step in this kind of research is the analysis of the microwear traces that occur on both experimental and archaeological tools. Archaeologists have a variety of methods available to them for this purpose. The first is visual assessment with a low-power stereo microscope. This is fast and thus allows fairly large sample sizes. It's also pretty effective for detecting tiny fractures and crushing along tool edges, and things like impact fractures on projectile points, but it's not suitable for assessing polish or striations. For that, we need the kind of imagery we can get with a high-power metallurgical microscope. It takes longer to assess each specimen, but it provides good images of polish and striations. Here, for example, you can see the kind of polish that occurs when the contact material is antler. This polish comes from using a flint sickle to cut through reeds. However, a downside of both low and high power microscopy is that they require subjective assessments of the wear and polish that can be seen in the image. Several newer methods measure surface topography or texture, allowing quantitative assessment of surface wear and polish. In this example of confocal microscopy used on the edge of a tool that was used to scrape hides, we get quantitative measurements over a small area of the tool edge. This can facilitate statistical comparisons against other tools. For example, where the sample sizes are large enough, you could conduct an analysis of variance of the results, with the allocator or manager of the study disguising the nature of the groups until after the analysis is finished.
In this video, I wasn't able to give you a very thorough demonstration of use-where analysis, in part because of pandemic restrictions, which required me to do the video all by myself, when in reality a proper use-where study would involve experimental controls, multiple people, randomization, a lot of microscopic work, and so on, which isn't really available to me at the moment. So what I've tried to emphasize is kind of general issues that you should be thinking about if you're deciding to do a use-where study, including how to impose those kinds of controls to ensure that your conclusions about use-where are valid ones.
If you'd like to learn more about use-where analysis and experimental design, you could check out chapters 6 and 11 in my book, The Archaeologist's Laboratory, available from Springer, and also the references cited there. You might also like to check out this book on use-where and residue analysis, also available from Springer. If you'd like to be alerted as I publish new videos on archaeological laboratory analyses, please click on the subscribe button down below. Thank you, and stay safe.